Welcome back. So the last time we just started the a discussion on the implicit function theorem, the motivated question being, if you have like say 20 equations and 35 unknowns, would you expect to have 15 free parameters, right? This is the question, if they're nonlinear equations. So to this end, let's look at an example. Yeah. So let's take x square plus y square equals 1. So of course, this is the case. So this example already tells us something interesting. So this is one equation, two unknowns. The solution need not be unique. That is, you can have more than one solution. Locally, one can hope for a unique solution. Locally, one can hope for a unique solution, not always though. So for example, what is this? This is just the circle, right? If you look at this point, that is near the point x equals 1, no matter how small a neighborhood you choose, you will have two solutions, right? The vertical line test will fail here. Okay, one can only hope, but the hope need not manifest as reality. Okay, right. This is one problem. Another problem is can fail to be differentiable. So for example, if you take near the point x equals 1, if you take this thing, near x equals 1, the solution, I mean of course, this x equals, first of all, this is a slightly unfair question because at x is not allowed to be larger than 1. So if you are near x equals 1, you can only talk about differentiability from the left, but even that fails, right? The last observation we want to make is that it might help to change the roles of the dependent and independent variables. What does this mean? See, near this point, you can obviously not solve for y in terms of x because there is no unique solution. It won't behave well, right? It is not differentiable and so on. But you can solve for, near this point, you can solve for x in terms of y. You can still write x as square root of 1 minus y square, and this is perfectly fine, right? It behaves perfectly well near this point. So if you just give me some arbitrary equation, it's not always clear that as to what the independent variables are and what the dependent variables are, even locally. Okay, that's what this example illustrates. Okay, right. Let's look at another example. This is far more complicated. Now obviously in this case, it's going to be extremely difficult, even impossible, very likely impossible, to find a formula to solve for one variable in terms of the other. If you want to solve for y in terms of x, right, if you fix x, you will be solving a very complicated equation that is not even a polynomial. Likewise, if you fix y, again for x you are going to solve an equation which is not a polynomial. So it's going to be very complicated. So it's very likely that there is no explicit formula you can write for the solution, even if there is a solution at all. Okay, even if we manage to prove that y is some function of x for some nice, let's say, differentiable function of x, g of x need not have a nice formula. That is, it's not explicit. Okay. By the way, this nice formula, you can make these sorts of things precise. I mean, obviously that's not our goal. We will not be interested in that. But if you are interested, you can look up something called differential Galois theory if you want to look it up on Wikipedia or some such thing. Okay. Anyway, the point is, you can, so at the very least, can you prove that y is equal to g of x even locally near some point? Is that at least possible? Even if g of x may not have a nice formula, does there exist a function g of x in the first place? That's also not obvious, right? Okay, so near the point x equals 0, so if you take x equals 0, you'll get 0 plus y square plus e raised to y raised to 4 times 0 equals 1. So y is plus minus 1. Okay, so this is a point that lies on this set. Okay, so at least near, let's say 0 comma 1, let's say 0 comma 1. Okay, what happens, right? So x square plus y square plus e raised to y sine square x cube equals 1. So suppose you want to solve for y, right? I mean, had this not been there, we could have simply written y as square root of 1 minus x square, but we have an error term, right? You will obviously have an error term. Now this error term, if you wish, is going to be roughly like x raised to 6 in some sense, right? Because this is roughly like x raised to 6. This is approximately e, right? Y is approximately 1, so this is approximately e. So this entire thing is roughly like x raised to 6, okay? It's such a small error that you can probably hope that indeed y can be solved for in terms of x. So the hope is y equals g of x near x equals 0, y equals 1. This is the hope. Why? Because the error terms are very small. Okay. Right. So why don't we actually phrase this question a bit more precisely? So a question. Then, when can we expect that y can locally, that is near the point a comma b, be solved for in a C1 manner in terms of x? So the point is, you want to solve, you want to look at the level set f of x comma y equals c, and you want to solve for y in terms of x, right? So if f of x comma y is x square plus y square and c equals 1, you can solve for y in terms of x near many points, not all. So the question is, when can you actually solve for y in terms of x given f of x comma y is c and f of a comma b is c for some a and b, meaning near this point a comma b, can we hope that we can solve f of x comma y equals c and obtain y as a C1 function of x. Okay. This is a reasonable question to ask at least. Okay. So, what is the intuition here? You want to solve this, right? What is f of x y approximately equal to? It is f of a b plus the derivative at a b times x minus a plus the derivative at a b of y times y minus b. This is equal to c, right? So, these two c's will cancel out and you will say this plus this is approximately equal to 0, right? Which means we can expect to solve for y approximately in terms of x provided this is not 0. If this is 0, then we are in trouble, right? Then it is unreasonable to expect to be able to solve for y in terms of x in a nice manner. Okay. So, this then leads us to a theorem. Let f So, suppose you manage to actually solve for y in terms of x via a C1 function. So, what this theorem states is that suppose the answer to the previous question is yes, that is suppose you can solve this equation near the point a comma b if x is in a minus epsilon b a plus epsilon and let us say y is also in b minus some epsilon and b plus epsilon. Okay. So, near the point a comma b, suppose you can solve for y in terms of x in a C1 manner. Assume that this derivative, partial derivative is non-zero, then you can find a formula for the derivative of g. This theorem is probably known to you. This is called the technique of implicit differentiation in one variable calculus. If you want to find the derivative of a function which is defined using another function, then you can do this by using partial derivatives. This is called the technique of implicit differentiation. Okay. This is easy to prove using the chain rule. You simply differentiate this with respect to x by assuming y as a function of x, that is if you take this equation and you simply differentiate this using the chain rule, then you will easily arrive at this formula. Okay. So, this is an easy thing to prove. What is harder is with this assumption alone, you can come up with a g of x so that you can solve f of x y equals c. With this assumption alone, you can prove that g of x exists. That is hard. if you already know that g of x exists, finding out its derivative is just a matter of applying the chain rule, and I urge you to do it on your own. I won't do it. Okay. So the question is, why does g of x even exist? That is the real question, which is basically our previous question. Okay. Right. So here is the first version of the implicit function theorem. It's basically an affirmative answer to the previous question, that's all. Okay. This is open. And then there exists a neighborhood of the form a minus epsilon, a plus epsilon cross, b minus, let's say, epsilon tilde, b plus epsilon tilde, such that, and perhaps, and a C1 function g from a minus epsilon comma a plus epsilon to r, in fact not all of r, to b minus epsilon tilde, b plus epsilon tilde, such that which is contained in U, such that f of x comma y is C on this neighborhood if and only if y equals g of x. So this is the implicit function theorem in two variables. This is exactly the answer to this question. That is, the answer to this question is, when can we expect it? Precisely, the answer to that is precisely this being non-zero. Okay. So once again, what is it saying? If we have a C1 function of two variables on an open set, suppose f of AB equals C, and this crucial condition holds. Okay. This is in some sense, intuitively, it's simply saying y f actually depends non-trivially on y. The derivative with respect to y is non-zero. When is the derivative with respect to y 0? For example, if f doesn't even depend on y, suppose f of x comma y is a constant in y, that is, suppose f of x comma y equals x, then can you solve x equals c? Sure. But can you find y as a function of x uniquely so that x equals c? No, of course not, right? So this is in some sense telling you that f depends non-trivially on y. Anyway, under this assumption, there is a neighborhood of the point a comma b in R2 of this specific type. There is a rectangular neighborhood, if you will, of a comma b in R2, and a C1 function of x, so that f of xy is c and xy is in this neighborhood if and only if y equals g of x. So you can implicitly solve for y locally in terms of x. This is the implicit function theorem in two variables. As you can very well imagine, you can have an implicit function theorem in more than two variables, which is also something we will do soon. But this is the starting point to understand the statement as well as the proof technique. Right. So basically, given x, we want to solve f of x comma y equals c for y. Right. The point is, the inverse function theorem does something like this, right? It solves a collection of nonlinear equations. The only trouble is, in the inverse function theorem, what the inverse function theorem says is you can solve, if you have n equations and unknowns, you can solve it provided you already have a solution and you change the right hand side a little bit. Here the right hand side is not changing, it's fixed, right? So what we want to do is to convert f of x y equals c into two equations where one of them is used to solve for x. See, the inverse function theorem would say that if you change the right hand side a little bit, I can find a left hand side that works, right? So unfortunately here you have two variables and you have only one equation. So why don't we convert it into two equations so that we can use the inverse function theorem? How can you convert it into two equations? Here's a stupid way to do it. It's a very silly way. You simply, the equations are just these, right? In other words, the first equation is just x equals x, it's not saying anything. But by adding this trivial equation, we have now gotten a map from R2 to R2. And therefore, we are in a good position to try to use the inverse function theorem. Let's call this h, that is h of x y equals x comma f of x y. Right. So we want to use the inverse function theorem. So let's, h is obviously, if f is CR, h is also, by the way, this is 1 is a red herring here. This 1 can be replaced by anything. It can be CR if you wish. Okay. The 1 is not so important. But we will still keep it as 1 because that's easiest for us to understand. Okay. So what's the derivative of h at the point a comma b? Well, what is the derivative matrix? It's the gradient of the first component, which is 1 comma 0, and the gradient of the second component. This is not 0, which means the derivative is an invertible matrix. Why is it invertible? Well, you can compute the determinant, of course. The determinant is 1 times this minus 0 times this, and this is not 0, so the determinant is not 0. But even without using the determinant, you can say it's invertible. How? Recall that when is a matrix invertible? When all the rows or all the columns are linearly independent. These two columns are obviously linearly independent. Why are they linearly independent? Well, if you take C1 times this plus C2 times 0 comma this, right? If it's 0 0, then obviously C1 is 0, and since this is non-zero, so is C2. Okay. Why am I saying this instead of using the determinant? You will see in a moment when we go to the proof of the more general implicit function theorem, it's easier to do it this way. Anyway, so the bottom line is, by the inverse function theorem, H is a local C1 diffeomorphism. What does that mean? What that means is, if you take this equals say P comma C, this can be locally, by locally I mean near the point A comma, near locally solved for, in the sense that near the point A comma C, if you wish, can be locally solved for x comma y in terms of p comma c in a C1 manner no less. Okay. In other words, so you can basically solve this equals p comma c as a C1 function. So x equals p, f of x comma y equals c, which means f of p comma y equals c if and only if y is a C1 function of p comma c, which is a C1 function of x comma c, because x and p are one and the same. So in fact, not only have we proven that you can, so we have proven the inverse function theorem, we have proven something even stronger. We have shown that f of x comma y equals c on this neighborhood if and only if y is not merely a C1 function of x, but actually it's a C1 function of x and c taken together. It's a C1 function of two variables, x and c. It's of course a C1 function of x if you fix c, but it's even better than that, right? So the proof is showing something even better than what we want. Okay? So that's the implicit function theorem in two variables. Right. So the proof is to apply the inverse function theorem in a clever manner to implicitly solve for one of the variables in terms of the others. Let's do the more general implicit function theorem. Rm CR function, of course r is greater than or equal to 1. Suppose f of a comma b, where a is a vector, maybe I'll put a vector sign just this one time. A is a vector in Rn, b is a vector in Rm, equals c, and the derivative matrix of f with respect to the y variables, these are the x variables, these are the y variables, at the point a comma b is invertible, then there exists a connected neighborhood A inside Rn of A and B inside Rm of B, such that A cross B is contained in the domain of F, and there exists a unique CR function G from A to Rm such that f of x comma y equals c on A cross B if and only if y equals g of x. So this is a long statement. Let's try to decode what this is saying. It's saying if you have a function of, maybe I'll put a vector sign here as well. If you have a function to Rm, so what the aim here is to solve this. You have m equations and n plus m unknowns. Okay, this is n unknowns, this is m unknowns. So you have m equations and n plus m unknowns. So, and you already have one solution to this equation, namely a comma b. The idea is, near a comma b, do you have more solutions? And not only that, can you solve for some of these variables in terms of the other ones in a CR manner? And the answer is yes, provided this holds. What is this curious little condition? If you fix x and you differentiate with respect to the y variables, this is an m by m matrix. So, it makes sense to ask whether it is invertible or not. And if that is the case, then indeed you can solve it. This is the analog of if y was not really a vector, if n and m were both 1, then this is a 1 by 1 matrix, namely just asking whether df by dy at this point is non-zero. Okay, it's an invertible matrix. So, a 1 by 1 matrix is invertible if it's just a non-zero number, right. So, this is the generalization of the previous theorem, and in fact, as we shall see along the proof, we can actually say that y is not just a C1 function of x, but a C1 function of x and c taken together. So, if you vary this also, y changes in a CR manner, sorry, not C1, CR manner. Okay. Right, so this is the very powerful implicit function theorem, and we will give the proof of this the next time. So, we shall stop over here. Thank you for joining.